All right, the question that motivates today is, can we divide matrices? Right? And the answer is, well, kind of. Yeah. So, thank you guys. Okay. So, again, your note sheet is just a copy of what I have up here. So when it comes to the examples, we'll be writing lots. But until each example comes, you may just be highlighting and making annotations along the way in whatever way serves you, okay? So this should be just exactly what's on yours too. So I want you to start by realizing the fact that really division, in any sense that you've ever thought about it, is actually a fiction, isn't it? Like you can actually do in your life just fine without ever thinking about division, am I right? If you ever want to divide by 5, you just multiply by 1/5, right? Like you never need division actually. All you need is multiplicative inverses, don't you? That is, I want you to understand that by 5 to the negative first, like the inverse of 5, that's just the thing that solves this equation, right? 5 inverse times 5 equals 1. So what is this thing? Well, we happen to have a name for it. It's 1/5. But we could also just call it the thing that makes this equation true, right? The multiplicative inverse of 5, right? And every number, you know, has a multiplicative inverse. So the question still is, like, does this happen with matrices too? Is there any notion of like an inverse for matrices? But before we can even ask that question, we need to establish what do we even mean by 1 in the matrix world. But I think we've already answered that today in the warm-up. What is 1 for matrices? What is it that when you multiply by it, seems to leave things unchanged? Did you see it? It was matrix A in the warm-up, right? For a 2x2, you just saw it. It's 1, 0, 0, 1. Or in general, it's called the identity matrix, and it looks like this. It's in your note sheet there, right? It's for any size here, it's an n by n square matrix, which is all zeros except ones on the main diagonal, okay? And you'll find, we haven't proved this to be true. You could maybe prove it though, I don't know. You'll find that this multiplied by any square matrix of the appropriate size will do nothing to the matrix. And like Ian, you found out, this commutes, right? It's, if we multiply this on the left or the right side, you still get the same thing, right? So that's great. That's called the identity matrix. So we now answered the first question, and that's what do we mean by 1, or what do we mean by the multiplicative identity in this new world of matrix multiplication? And the answer is now before us. Okay, great. So now we can finally formulate the question that we had in mind earlier. If I have a matrix A, what matrix do I have to multiply by to get the identity? Right? Isn't that really the question? It's just like asking what times 5 equals 1. And the answer we know is 5 to the negative first. But what is it for matrices? That's a little bit harder, but we can maybe actually solve this. Let's actually do this. For this example, let's find together the inverse of 1, 2, 3, 4. Okay? So again, we're desiring some matrix. There'll be a 2x2. It needs to be a 2x2. Times this, and I want that to be the identity. So let's read this carefully, very carefully, off of what this says. How do you do matrix multiplication? Oh yeah, that's right. Row by column. You get the song forever in your head. Okay, so we're going to do this row by this column, right? So what happens when we multiply this row by this column? We should get 1, right? X plus 3y. Shouldn't that end up being whatever x and y are? Shouldn't that end up being 1? X plus 3y. Good. Let's write that down. X plus 3y equals 1. Great. Shouldn't it also be true that 2x times 4y ought to be 0? Okay, great. Let's write that down. And let's write down all 4 of those similar statements right here. And now I'd like you to figure out what x, y, z, and w are. Ready? Go. So solve this system. It's kind of a system of 4 equations, right? Kind of not, right? Just if you look at this, can you see that just the first 2 equations? Just the first 2 equations will quickly admit what x and y are, right? And the second 2 equations will admit what z and w are. So how about we have all the people on the outside of the room, on the outside edge, solve for x and y, and everyone on the inside here in the court, you guys, let's all do z and w, okay? You can figure out what z and w are. Okay. In the inside here. I'll join the z and w people. And if you finish your task, you can turn to the other letters you didn't solve for and try that. Or you can just take the other people in the classroom's word for it. Oh, this is supposed to be a 0. Wait, I messed up. This is supposed to be a 1. How'd you do? X, Y people, did you do okay on the outside? What'd you come up with for X and Y? X equals -2 and Y equals 1. And we found in the middle, didn't we? Can someone check my work? Middle people.
Okay, I got that.
We found that Z and W were 3/2 and -1/2. That is, I think that the inverse matrix is this. That's what we're just saying, isn't it? Isn't that what we solved for those 4 constants, didn't we? So I think this is the matrix that does the job. I think that's the inverse. I think if we multiply this by 1, 2, 3, 4, that we get the identity is what I'm saying. Or maybe the other way, too. So next page I actually have this worked out. The answer is right in front of you, actually. Okay? Is this really the inverse? Let's try it, right? It's very quick to check. So is it true that A inverse times A does give you that identity? Just check it with me quick. Right, here we go. -2 plus 3 is 1. -4 plus 4 is 0. 4. 3/2 and -3/2 is 0. And 3 and -2 is 1. Yes. Yeah, you like that? So it works. Feel free to try it the other way too. A times A inverse. Does that work? You can test it. You'll see that it does in both directions. A times A inverse and also A inverse times A in both cases give you the identity. So I think we've done it right. That's a great test to see that it worked. And by the way, we can do that on the calculator too if you like. Your calculator, well, we'll do it in a second. Whatever. The inverse of a 2x2 matrix in general is written there on your paper. This is just what happens if we did the last experiment with, instead of 1, 2, 3, 4, A, B, C, D. If you solve it just in general, once and for all, this is just what you get. I have every confidence that you guys will be able to come up with this too. It's just the process we just did, formalized. Okay. Now read it carefully, make sure you see what it says. This is A and D switched, so you take your matrix and you switch A and D. You don't switch B and C, but you make them negative. You make them the opposite of whatever they were. And then you multiply everything in your matrix by 1 over this quantity, AD minus BC. In fact, for the example we just did, verify that that works. Is that to give us the inverse of 1, 2, 3, 4? What would the inverse of 1, 2, 3, 4 be? We claimed it was up at the top here, this. -2, 1, 3. Does that work here? Try it. Does it work? So apparently the inverse of 1, 2, 3, 4 is supposed to be gotten by using this formula. Is this also something that gives the answer? Let's see here. So we switch these, we negate these, and then we multiply by 1 over something. What is that? A times D, which is 4, minus B times C, which is 6. So what does that come out to be? -2. Is that the same thing? Let's multiply it in. You get -2, +1, 3/2, and -1/2. Ah, yes, good. That is what we have up there, isn't it? So anyway, so this is a cute little formula that works. For higher order matrices, your calculator does a great job, but you can imagine how you would find it. You can use the process we did, everyone just collectively just did a second ago to find the inverse. You could do that with a 3x3 too, couldn't you? It would be a terrible system of equations to solve, but there's no reason that you couldn't like teach a computer to do it. And that's what your calculator does for you too. So also check with your calculator here. Yeah, let's get our calculator to do this problem too here. We're just having so much fun with the calculator. Let's go to A. Let's make this 1, 2, 3, 4. And then if you do second matrix A inverse, let's see if we get the right thing. Let me say it's a fraction. Is that what we got? Pretty cool. And if you do second matrix A inverse times matrix A, what should you get? The identity, right? So I hope you see how these things can be done in your calculator too. When you're ready, try the next two problems that are there for you that ask you to find the inverse. I made one small change to problem B. Do you see my change to problem B? Crazy stuff right now. When you're done with these two problems, there are a lot of fun activities you can do after doing these two problems, right? If you claim you found the inverse for A, check it by hand, multiply it by the original matrix. See if you get the identity. Or multiply it by the other way, right? Multiply this by your inverse and see if you get the identity. Multiply both ways. Check with your calculator. See if it gives you the same numbers. Right? Lots of different things you can do after you're done with it. Check with a neighbor. Sing the song. Great. Done with the first one?
Yeah.
Well, you're finding it by hand. Well, that's intense. You can use the formula, man.
I know. That's great. No, I don't do negative. Yes, I successfully
You
avoided
get the inverse for the first one. You get the welcome to math class. Good to have you. Like I said, when you're done, check it. Multiply your purported inverse by the original matrix and see if it works. Try it on the calculator, see if it works. As you do that, like 1 over AD minus BC, does that feel familiar at all to you? That whole AD minus BC thing? Maybe not, I don't know. It's not the cross product, but we have done it before. We'll talk about it in a second. Did you notice that sometimes the inverse isn't defined? Did you see that on the previous formula I gave you? The 2 by 2 inverse is 1 over AD minus BC times whatever it is, D negative B negative C A or whatever, right? Yay. By the way, that's painted in the hallway down here too, the inverse of, you'll see it down there. One of the equations is the inverse of a 2 by 2 matrix. Go look for it now that you've seen this equation. But did you see at the very beginning of that, it's what it said? It said if, it says it right on your paper, if AD minus BC if AD minus BC is not 0. Why do we have to require that AD minus BC not be 0? Because it'll make that denominator 0. Isn't that a problem? Because the formula calls for us to do 1 divided by that. So that's a problem. So does that ever happen for a matrix? When does that happen? How about this one right here? Oh, is that what you're saying? Okay. So it's possible for the inverse to not exist for certain kinds of matrices, like this one. If AD minus BC comes out to be 0, then we call that a singular matrix. So that word is on the previous slide. We just didn't highlight that. So if it doesn't have an inverse, then we call it a singular matrix. It's alone. This doesn't usually... Can you think of any numbers that are singular in the real number system, like that don't have an inverse? That don't have a multiplicative inverse? 0 doesn't have a multiplicative inverse, right? So this matrix is kind of...
One would be its own.
Yeah, one is its own. Yeah, that's fine.
I mean, if they just
All
kind
right.
of use a prime number, that's bad.
No, it's fine.
That and because we do that on there.
All right, so the quantity, listen please, thanks. The quantity that we were just talking about that seems to be so characteristic, so important for us, we like to actually give a name to it. It's called the determinant of a matrix, okay? And you've already stumbled on one of the important things about the determinant. It says whether the matrix we're dealing with has an inverse or not, yeah? If the determinant is 0, and I'll just tell you right now that this generalizes for larger matrices too. A 3 by 3 matrix also does not have a determinant. It does not have an inverse if its determinant is 0, or in general an n by n matrix. So the determinant provides a little bit of a test to see if there even is an inverse. So in the case that we were just working with, that's just AD minus BC if we're working with a 2 by 2. And you could write it a number of different ways. Sometimes we write det A, like determinant. That's how your calculator has it. If you want to take the determinant of a matrix, you do det and then parentheses, and inside put matrix, the matrix you want. Sometimes we use, do you notice here? These are not the kind of the brackets. These are vertical bars. So we're kind of stealing absolute value notation in some sense. The determinant, we haven't really talked about why this would be true. In some sense, the determinant does give kind of the size of a matrix in a certain way that we haven't really talked about, but there is a magnitude maybe happening there somehow. The determinant of a 3 by 3 matrix is there in your notes, and by the way, I think there's a small typo here. This should be at 2, 2, 2, and 2, 3, 2 there.
Yeah.
But does this look familiar? Yeah, this should, right? I mean, that was the cross product. We should have maybe like done this first, right? But the cross product is a special case of this where we have like I, J, and K loaded into the top row. But in general, this is how you take the determinant of a 3 by 3 matrix. And in the end here, we come out with just one number, right? Because in the end, these are each of these determinants you're going to compute. And then you'll have a number times a number, and you'll add all these things up. So you can do a 3 by 3 determinant by hand. You already know how. And higher order matrices can actually be computed using a similar rule. You can imagine how that would look. You'd go across the top row of a 4 by 4 matrix, and you'd multiply each element by the determinant of the 3 by 3 minor matrix that remains, right? So can you imagine that? And then you'd have a whole bunch of 3 by 3s. It would look the same kind of calculation. Each one of these would be a 3 by 3 instead. You can imagine. It also turns out, though this is not, I'm just telling you for fun. If you want, you can actually expand across any row or any column. We have these cofactors associated with this. There's something called the cofactor matrix. It's kind of like a grid of pluses and minuses. And if you associate pluses and minuses with these in this grid pattern, you can actually go down any row, try it, any row or any column, and expand and use the, like if you went down this column, you could use this one times this determinant minus this one times the determinant of the remaining matrix there, plus this determinant times this guy. Right? You can go down any row or column, actually. It's cool. Anyway, give it a try on this guy, and then when you're done, actually check it using technology. one of these is another determinant to do, a little 2x2 determinant to do. Boom, boom, right? So in the end, your answer should be one number again for the determinant. Okay? You should get a number like 5 or negative 5 or 27. One number. Feel free, like I said, to check with technology when you're done too. It says check with your calculator. Try that. Just to practice the calculator feature, not because it's super important, but just because you could try playing around with the calculator. Yeah, they're like these vertical bars, actually. Okay. You didn't finish it quite good. Is there 41 too?
I got 18. I got 18. Can you show yours? No, I don't. Please. No, I got 18.
You actually love getting it. You do.
I don't like that.
Help your neighbor out with this calculation.
That hurt. My phone was in my pocket. I'm working on the problem right after.
Good. You ready for that?
A little.
Good. Here he goes. Man of legend. Did you get 18 like Franklin did? Check with your calculator, it should give you 18 as well. Did you figure out how to do that on your calculator? Again, on your calculator you'll type in, you can get this command on the math menu under Matrix. You'll type this in, if supposing you load this into A, and it should give you 18. That A, try it, see if it gives you 18. Are we good? Are we ready to move into the next problem? All right, here we go. So let's practice our inverses in this new interesting situation. First of all, is it even reasonable for me to ask you to solve this equation? Is this a 2x2 times a 2x1? Does that even equal a 2x1? Yeah? I think so. Yeah, I have to think about that. But yeah, I think that makes sense. I just want to make sure it's certainly possible for me to throw a problem that, like this at you that doesn't make sense, right? The dimensions don't match up. But I think for both of these problems, it's going to work. It seems like there should be maybe an x and y that make this work. So I suggest a method in the directions, and that's to multiply both sides of this equation by the inverse of this matrix. So, I don't know, figure out what that is. And we're going to, whatever it is, I don't know what it is yet, we're going to multiply that by the left side on both sides. So now I need to compute the inverse of that thing. What is it? let's see, it'll be 3, 2, negative 3, negative 1, times 1 over the determinant. 6 minus 3. Yeah, did you get this for the determinant? Excuse me, the inverse? So maybe I'll move that 3 in there. Did you get that for the inverse?
Sure.
Are you talking about the same matrix I am? 2, 3, 1, 3?
Exactly, that's what makes me feel your work, okay?
2, 3, 1, 12.
Well, I forgot why you did 4 there, is that right?
So we just need to work out both sides here, see what we have left. You get the inverse? Someone check me on my inverse. Yeah, that's what you got. Okay. When we multiply these two matrices, what should happen? Hopefully we get the identity. Let's just check that we do. Negative 2 minus 1 is 1. Yay. 3 minus 3 is 0. Negative 2/3 and 2/3 is 0. Negative 1 and 2 is 1. Yay. All right, that worked. Good. So far, so good?
Yeah.
Multiplying over here is a little trickier, but we'll do that. What do we get on the, what do we have on the left side, really? What happens when you multiply this matrix by this? We get another 2 by 1, and it's just what?
XY.
Yeah, it's just xy. I hope you understand why left multiplying by the inverse is a great move here, right? Because what it does is effectively take this out of the picture, right? I hope you see that really it's like solving this equation, right? How do you solve this equation? You multiply by the inverse of 5 on both sides, don't you? That's essentially what we're doing right now here. This multiplying by the inverse like destroys this guy right here, okay? So now we just need to work out what this is. What do we get? 6, negative 9 is negative 3, and negative 2 and 6 is 4. Check me on that. Did we do it? All right, so we figured out what this vector is, xy. It's negative 3, 4. Yay. The column matrix, which is just another word for a vector, yeah. That's a great point. In fact, so I think we're ready to ask this question. Thank you, Vivian. What Algebra 1 task did you just accomplish? What are you saying? What are you suggesting? That this is really just us solving a system of equations? Oh. We'll come back to B in a second here. Yeah, she's right.
Don't go back to B. There's no point.
Don't go back to B?
There's no point.
Did anyone solve B?
You can.
Yeah, yeah. I think you'll find that this doesn't have an inverse, which means this doesn't have a solution, right? All right, so let's go back. Let's talk about that first one we just solved together, right? What did we just do? Well, by the definition of matrix multiplication, isn't the original thing? Couldn't it be written this way? Because we have 2x plus 3y. That should be 6, and 1x plus 3y. That should be 9. So we really do have what Vivian said. We have this system of equations. So I hope you realize that really what we just did is not just solve a matrix equation, we also solved a system of equations. And we just saw that the way to solve a system of equations with matrices is turn your system into a matrix equation, first of all. And then use the inverse. Multiply by that on both sides on the left, and you'll get your solution. So this is powerful. The reason you might be thinking, like, I'd rather just do the old thing. But this suggests a very powerful way to solve this equation in general, especially if we let our calculator do it. So I'd like together to do the last one, which would be a little bit intense to do by hand, but with our calculator, it takes just a matter of seconds, right? So really, as a matrix equation, isn't this 2, 3, negative 1, negative 1, 1, negative 3, 1, negative 4, 0?
Sure.
times x, y, z.
Oh, yeah.
I mean, isn't that the same thing as a matrix equation? And in matrix land, solving this huge system of equations is as simple as solving 5x equals 3, right? It's just multiply by the inverse on both sides. I hope you see, like, with one move, we can solve an entire system of equations. It's a powerful idea. It does take loading it into your calculator, I guess, but. So whatever the inverse is, you can figure that out on the calculator. Multiply the inverse by. And in a second, you'll have your answer. So load this into a 3x3 matrix on your calculator. Load these constants into a 3x1 vector in your calculator. Maybe A and B. And then just multiply in your calculator A inverse times B. And it'll out will spit your calculator a 3x1 matrix, which contains what x, y, and z are. Like G. Could you do this with a 5x5 matrix? Easily, right? A system of 20, 20 equations, 20 unknowns, not a problem. I hope you see, like I said, the power of the matrix representation. If someone gets this, let me know. I don't know what it is off the top of my head. Figure it out. Negative 5, 1, 18, she says. Okay, so go back, feel free to try this. If you plug in x equals this, y equals this, and z equals this into any of the original equations, you'll find that those satisfy all the original equations. Okay. Are you clear on what the homework is tonight? I don't have it written up there, sorry. It's on the first slide though. I'll take you back to the first slide here. There it is right there. If you didn't write it down, take a picture, write it down quick, something. Again, it's from the book. Tomorrow, thanks, Shadows, for hanging out with us. Great day, guys. Thanks for participating in the lesson. Very good.